Hello everyone, once again welcome to our physics class. So within the previous sessions we have completed our chapter waves. Hope you might have gone through the beats, beat frequency and all those derivations. Today we are going to start our new chapter, that is chapter 10, mechanical properties of fluids. We had already discussed mechanical properties of solids in our chapter 9, mechanical properties of solids. So unlike a solid, a fluid has no definite shape. You know that. Fluid means liquids and gases together constitute fluids. Okay, so a fluid, that means both liquids and gases, has no definite shape. Fluid is that which can flow. A fluid has no definite shape. It assumes the shape of the container. And what is the main difference between the liquids and gases? Even though liquids and gases are commonly called as fluids, there are some differences between liquids and gases. Liquid is incompressible, while a gas is compressible. Liquid has a free surface, while a gas has no free surface. Okay, so these are some of the differences between liquids and gases. So fluids can be defined as any substance which is capable of flowing. They don't have any shape of their own. For example, water, which does not have its own shape, but it takes the shape of the container in which it is poured. But when we pour water in a tumbler, it takes the shape of that tumbler. Okay. Both liquids and gases can be categorized as fluids as they are capable of flowing. Volume of solids, liquids and gas depends on the stress or pressure acting on it. In this chapter, we will study if we apply force on the fluid, how does it affect the internal properties of fluids. Fluids offer very less resistance to shearing stress. So the first topic that we are going to discuss in this chapter is pressure. You know that a pressure is inevitable whenever we discuss fluid. So in fluids, the molecules are free to move. When they move, they collide with the walls of the container and exert some force on the walls. And this force is acting normal to the surface. So the force acting per unit area normal to the surface is called pressure. Okay, so what is pressure? Pressure is defined as the force acting per unit area. Okay, and also this force will be a normal force. Normal force means force acting perpendicular to the surface. And what is the expression? Pressure is equal to force by area. And if we consider very sharp needle which has a small surface area and consider a pencil whose back is very blunt and has more surface area than the needle. Okay, so which is more sharp, a needle or the pencil? Yeah, needle will be more sharp because the pressure exerted at the tip of the needle will be more than the pressure exerted at the back side of the pencil, because the area of the tip of the needle is less, and wherever area is less, pressure exerted will be more. So the effect of force exerted on that area also will be more. Okay, so if we poke the needle in our palm, it will hurt as needle gets pierced inside our skin. But if we poke the blunt side of the pencil into our hand, it won't pain so much because the pressure exerted on the blunt side of the pencil will be less and it is not able to pierce inside our skin. Okay. Then pressure in fluids. Normal force exerted by the fluid per unit area, that is pressure. So if we consider a container and it is filled with water, and if we insert any object, let it be a ball, inside the container, this water will exert normal force onto this object from all sides, isn't it? So this normal force exerted by the fluid on all sides of this object is pressure. So the normal force exerted by the fluid per unit area is pressure. This means force is acting perpendicular to the surface of contact, isn't it? Here this force is acting perpendicular to the area and this force is acting perpendicular. This force is acting perpendicular to the surface. Okay, so that is the normal force. Now consider a body submerged in water. Force is exerted by water perpendicular to the surface of the body as I shown here. Okay, so this normal force exerted by the fluid per unit area of the object is known as pressure exerted by the fluid. Okay. Now since fluid is at rest and body is submerged in the fluid, there cannot be motion along the horizontal direction, isn't it? So in the previous example in which water was taken in a container, the fluid or the water was at rest and the body is completely submerged in that fluid. So there cannot be motion along the horizontal direction. That means that that fluid cannot flow in the horizontal direction because it was a static fluid. Therefore, we always say that the force is applied perpendicularly. Now, pressure is a scalar quantity. Because of the force, there is not a vector quantity, but it is the component of force normal to the area. Because since force is present in the equation to find out pressure, we will think that pressure is a vector quantity. But we are not concerned about the whole force. We are just concerned about the component of force which is acting normal to the object. Okay, so component of a vector will be a scalar. Hence, pressure is a scalar quantity. Now, what is the unit? Unit of pressure is Newton per meter square or Pascal. Then another unit is there which is known as ATM. And ATM means atmospheric unit. It is defined as the pressure exerted by the atmosphere at sea level. And you might have already studied about this at ATM and all those units of pressure in your lower classes. So it will be just quick review of all those things. So atmospheric unit is or atmospheric pressure or atmosphere. That atmosphere is the unit. So atmosphere is defined as the pressure exerted by the atmosphere at sea level. And it is a common unit of pressure. So how will you convert atmosphere to Pascal? So Pascal is the SI unit. And how will you convert the atmosphere unit to Pascal? So 1 ATM is 1.013 into 10 raised to 5 Pascal. So this is the example for pressure. Here you can see these arrows represent the force exerted by the water on the bowl, and these forces are acting perpendicular to the or normal to the ball. So this force will be pressure. Okay, this force acting per unit area of the ball will be pressure. Now, next we will discuss about variation of pressure with depth. So what do you mean by variation of pressure with depth? That means we are going to derive a relationship here, and from the relationship we will be able to identify the variation of pressure with depth. That means how does pressure vary with respect to height or depth. So all of you listen here, and all of you please be ready with your pen and notebook. It's a derivation part. So pause the video for a while, get ready for the derivation and try to do the derivation along with me. So on the screen you can see a figure. Okay, this figure shows that we have considered a fluid, and that fluid is in a container, and you know a fluid is at rest in that container. Okay, so consider a fluid at rest in the container. Now consider a cylindrical element of the fluid having base area A and height h. Okay, so inside the fluid, see here you can see, if you consider this as a cylinder, let this be a cylinder. Okay, and that cylinder is filled with water, and inside the water we have considered a cylindrical element. Height of that cylindrical element is h, small h. Okay, and also we have considered some points on the cylindrical element. The topmost portion is 1 and the bottom portion is 2, and the force acting on the point 1 in the downward direction is F1, and the force acting on the point 2 in the upward direction is F2, and both F1 and F2 are the normal forces. Hence this F1 and F2 will be equal to P1 and P2. So P1 is the pressure acting on the point 1. P2 is the pressure acting on the point 2. Okay. Then what is the area? Area of the cylindrical element is A. Base area of the cylindrical element is A. Now, what will be the force acting on the top of the cylindrical element? We know that pressure P is equal to force by area. So, what will be force? Force F is equal to pressure into area. Okay. So, here at the point 1, force acting at the point 1 will be F1. And F1 is equal to pressure acting at the point 1 into area. So, pressure acting at the point 1 is P1 and area is A. Okay, because base area is same for the points 1 and 2. So, no need to write A1, A2 like that. Then, next is force acting on the point 2. So, force acting at the point 2 will be pressure acting at the point 2 into area. So, pressure acting at the point 2 is P2 into area is A. And what will be the direction of these two forces? F1 will be acting downwards, F2 will be acting vertically upwards. Apart from this, one more force is acting here, that is weight of this liquid column or cylindrical column, and weight of the cylindrical column is mg. You know that weight always act vertically downwards. So, weight of the cylindrical column is also acting here and it will be acting vertically downwards. So, what are the total forces acting here? P1A vertically downwards, P2A vertically upwards, and one more force is there, mg vertically downwards. And the fluid is at rest because the fluid is inside a container, so it is at rest. Hence, the net force acting on the cylindrical element will be equal to weight of the cylindrical element. So, what will be the net force acting on the cylindrical element? It is F1 plus F2. But since F1 and F2 are acting in the opposite direction, we can write F1 minus F2 is equal to. So, this is the net force acting on the cylindrical element, F1 minus F2, and that will be equal to weight of the cylindrical element. So, weight of the cylindrical element is mg. Okay. And just substitute the expression for F1 and F2. F1 is P1A, F2 is P2A equal to mg. Instead of m, we can write, see, you know that density is equal to mass by volume. Isn't it? Density rho is equal to mass by volume. So, mass is equal to density into volume. So, we can substitute that expression here. So, mass will be density into volume into G. And again, volume will be equal to area into height. Isn't it? Area into height is equal to volume. So, again, here we can consider A as a common factor. So, here we can write P1 minus P2 into A is equal to rho into volume is A into H into G. Now, this A and this A will be cancelled and we are left with P1 minus P2 equal to H rho G. Okay, or P2 minus P1 as H rho G. So, this above equation, this equation shows that the pressure difference varies with respect to height H because rho and G are constants. So, the pressure difference depends only on height. So, as height increases, or height means the depth, as the depth increases, the pressure exerted by the fluid on the object will be more. It also increases. Okay. So, pressure is inversely proportional to height. And this pressure difference P1 minus P2 is known as the gauge pressure. Okay. Now, suppose point 1 is exposed to atmosphere. So, let's consider that case. Suppose here point 1 is exposed to atmosphere. So, we can consider our cylinder like this. Okay. So, here only point 2 is under the water. Point 1 has come out. So, now it is exposed to atmosphere. So, the pressure acting will be the atmospheric pressure. So, we can write P2, our expression was P2 minus P1 equal to H rho G. Isn't it? So, if point 1 is exposed to atmosphere, the pressure acting at the point, that is P1, will be equal to atmospheric pressure A. Okay, so we can write P2 minus atmospheric pressure. Now P1 is PA, atmospheric pressure, because atmosphere is exerting pressure at the point 1. So the pressure acting at the point 1 will be atmospheric pressure, and that is equal to H rho G. And if there is no P1, then no relevance in writing P2. So we can write simply P2 can be equated to P. Okay. So P2 is P minus PA is equal to H rho G. So this P minus PA is called gauge pressure. Gauge pressure. Okay. And from this expression, what is P? P is equal to PA plus H rho G. Okay. And this P is known as absolute pressure. Okay. So this P is known as absolute pressure. So that is gauge pressure and absolute pressure. Gauge pressure is the pressure difference, and this P is the absolute pressure. So however, pressure varies with depth or height. As the depth increases, pressure also increases. Now we can discuss the most important concept and also most interesting concept, that is hydrostatic paradox. See, hydrostatic means, hydro means water, static means rest. So we are dealing with the water or fluid at rest. And paradox means that something take place surprisingly, because we are expecting a result and we are observing a surprisingly different result. So here you can see 3 vessels, and 3 vessels are different in their shape. So their base area also will be different. So these 3 vessels A, B, C is filled with water or fluid, any fluid. And we can see all the vessels are filled with fluid to the same height, isn't it? So if we consider this as height H, so the height of fluid column in all the 3 vessels is H itself. Now we will expect that the pressure at the base of A, B and C will be different. Why? Because their base area is different. So we will expect the pressure at the base of the vessels A and B, C as different. But quite surprisingly, we can see that the pressure acting at the base of A, B and C will be equal. Why? If we consider this point in the vessel C, this much liquid column is exerting pressure at the point C or at this point, and similarly the height of the liquid column above this point is H. Height of the liquid column above this point is also H. And we know that pressure depends only on the height. Since the height of the liquid column above all these points are same, pressure exerted by that liquid column at all these points will be equal. So this shows that the pressure at ABC does not depend upon the base area or shape of the container. So this paradoxical situation is known as hydrostatic paradox. So the pressure exerted does not depend upon the base area or shape of the container. It depends only on the height of the liquid column above that point. So this is hydrostatic paradox. It's very important. So whenever you explain the hydrostatic paradox, you must draw this figure and then explain the paradoxical situation. Okay. Now what do you mean by atmospheric pressure? See, atmospheric pressure is the pressure exerted by the weight of the atmosphere. Atmosphere is a mixture of different gases, you know that. And all these gas molecules together constitute some weight. So by virtue of this weight, there is some pressure exerted by the atmosphere on all the objects. This pressure is known as atmospheric pressure. And value of atmospheric pressure at sea level is 1.01 into 10 raised to 5 Pascal. So 1 atm is 1.01 into 10 raised to 5 Pascal. You must remember this equation. Now next is, how will you measure atmospheric pressure? So atmospheric pressure can be measured by mercury barometer. And this mercury barometer is invented by an Italian scientist, Evangelista Torricelli. Okay, Torricelli. So Torricelli invented this mercury barometer. And the picture of mercury barometer is shown on the screen. It consists of a long glass tube closed at one end and open at other end. And it is inverted in a mercury reservoir. Okay, you can see this long glass tube, and this glass tube is closed at this end. It is open at this end. This glass tube is filled with mercury, and the filled glass tube is then inverted in a reservoir, and this reservoir also consists of mercury. Okay, so the mercury level inside the tube falls up to a height of 76 centimeter. Okay, the mercury level will falls up to a height of 76 centimeter. Now here consider 2 points A and B in the reservoir. So consider 2 points. Here we can consider 1 point. Let that point be A, and inside the tube you can consider another point B. Okay. Now these 2 points A and B are at same level, isn't it? Are situated at the same level, and we know the pressure acting at all points on the same level will be equal. So that means pressure acting at the point A will be equal to pressure acting at the point B. So that is what we have seen in the hydrostatic paradox. So the pressure acting at the point A will be equal to pressure acting at the point B, because both points are situated at the same height. Okay. Now what is the pressure acting at the point A? Whenever you see, if you look at this figure, you can see the point A is exposed to atmosphere, right? So atmosphere will exert pressure at the point A. So the pressure acting at the point A will be atmospheric pressure PA. And what will be the pressure acting at the point B? See, the pressure acting at the point B will be the pressure exerted by this liquid column of height h. Pressure exerted by this liquid column of height h. And that pressure exerted by a liquid column of height h can be find out using the expression h rho g that we have discussed just before. Okay, so the pressure exerted by a liquid column of height h is given by h rho g. So here point B is exposed to a liquid column of height h, that is a mercury column of height h. Therefore the pressure acting at the point B will be h rho g. Okay, so we got the expression atmospheric pressure PA is equal to h rho g. So using this expression we can easily find out or measure the atmospheric pressure. Thus mercury barometer helps us to measure atmospheric pressure. And in the experiment it is found that mercury column in the barometer has a height of about 76 centimeter. So height h is 76 centimeter at sea level. Okay, so 76 centimeter of mercury is equal to 1 atm. Then different units of pressure is torr. So 1 torr is also another unit of pressure. So 1 torr is equal to 133 Pascal. And bar is also another unit of pressure. 1 bar is equal to 10 raised to 5 Pascal. So you can note down these two units. Torr and bar are also another units of pressure. So 1 torr is equal to 133 Pascal. 1 bar is equal to 10 raised to 5 Pascal. You must know the conversion of these units to Pascal. So which are the different units of pressure? Pascal, atmosphere, torr, bar. Okay. Now, another device that we want to discuss in this chapter is open tube manometer. So just before we have discussed about pressure difference, isn't it? Gauge pressure. That gauge pressure can be easily measured using this open tube manometer. So let's discuss about the structure of open tube manometer first. As you can see in the figure, an open tube manometer is a useful instrument for measuring pressure difference, and this device consists of a U-shaped tube. Okay, you can see a U-shaped tube here, and this U-shaped tube consists of a liquid of density rho. So the liquid filled inside the U-shaped tube has a density of rho. Okay, now one end is open to the atmosphere, isn't it? This end of the U-tube is open to atmosphere, hence the pressure acting at that point will be atmospheric pressure. And the other end of the U-tube, so this end is connected to a system whose pressure is to be determined. So here this end of the tube is connected to a system whose pressure is P. So we want to determine this pressure, this unknown pressure P. Okay, now here how will you find out the pressure of that unknown system or unknown pressure of that system? So here also we need to consider 2 points, A and B. And here we can see point B is exposed to atmosphere, and also it is exposed to a liquid column of height h. So what will be the pressure acting at the point B? Pressure acting at the point B will be equal to the atmospheric pressure A plus the pressure exerted by the liquid column of height h, and pressure exerted by the liquid column can be calculated using the expression h rho g, where rho is the density of the liquid filled in that U-tube. Now consider the point A, and point A is exposed, or point A is connected to a system whose pressure is P. So the pressure acting at the point A will be P, because that system, this system will exert pressure at the point A. Now just look at the points A and B. Are they at same level, or are they situated at the same height? Yes. Here this is the height of A, this is the height of B. Both are situated at the same level, isn't it? So since the points A and B are at the same level, pressure acting at the points A and B will be equal. That means pressure acting at A will be equal to pressure acting at B. Now what is pressure acting at A? PA is P, that is equal to PB is PA plus H rho G. And we can just modify this expression as P minus PA is equal to H rho G. So here this term P minus PA is the gauge pressure, and this P is called the absolute pressure. Okay, so thus using open tube manometer we can measure the pressure differences, and we can also measure the gauge pressure, we can also measure the absolute pressure. So children, that's all about today's session. Notes of the topic and YouTube video have been uploaded. Just go through it. We will meet in the next session. Till then, take care all of you. Stay home, stay safe. Thank you.